Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular video, I'm going to look at a second version of representing the work done for a force which is going to be, of course, acting on a particle. And of course, we're going to see the relationship between this specific aspect of work and the kinetic energy. Now, in my previous discussion, I basically defined the concept of work, which was the product of a force and, of course, the displacement in the direction of force. And we had two specific representations for work done for, of course, a non-accelerated motion of an object and an accelerated motion, whereby we have decided that we can represent the work done between A and B for a non-accelerated motion given in terms of this specific representation, whereby we're going to have this one given in terms of the integral of this force element in the F and, of course, direction, and of course in the Y direction given as that. So this is going to be represented as such, whereby we had considered using this specific integral for the summation of elements between A and B. And of course, this was a description for the non-accelerated motion. Now, in our second case, whereby we considered the concept of acceleration from the Newton's second law of motion, we have decided that we can represent work in terms of this specific representation of the change in, of course, this element of kinetic energy, which we said that is going to be corresponding to the energy work theorem, which we have said, of course, in this specific case given as such. So in this particular video, we're going to look at a different way in which we can represent this aspect of work, which is going to be basically relying still on this specific aspect of a particle that is, of course, going to be having a change in kinetic energy. So from the fact that we had defined the concept of work as the product of a force given in terms of the integral of F dr. So in this case, we're going to borrow from this particular case, but we're going to consider a particular, of course, a force which is going to be directed in the x direction of particularly in one direction given as x. So therefore, we're going to find the work done in terms of the integral between 0 and, of course, this particular distance over x. And we're going to have this represented as a dr, generally given as that one. So again, we're going to borrow from Newton's second law of motion, whereby we're going to have this force represented as a product of mass and acceleration given as that. So therefore, we're going to have this specific aspect of acceleration represented in terms of a change in velocity over change in time. Now we can manipulate this specific formula and have a representation of this specific acceleration in terms of dv over dt is equivalent to, or dt over dt, and we're going to multiply that one with the value of dx over dt. And these are going to have a specific implication for this specific kind of evaluation. So in this case, we're going to have this one in terms of dx. So in a sense, if I have a number like a, and then I multiply this number times 1 over m, and then of course times m, this is going to be returning the value of that specific number. So if we consider this specific numerator and denominator for the first and second term, of course that's going to be giving us a dv over dt, and therefore that's going to be again one way in which we can represent this aspect of acceleration. And therefore I'm going to have this one implying that specific product. And therefore, we can still consider this acceleration being given in terms of this product of a dv, of course, as just as another version of this specific representation which we have given all over dx given as that one. And of course, we're going to have that one as a product with the v. So in this case, if we look at the second part of this specific representation, that's going to be giving us our velocity. And therefore, we're going to take from Newton's second law of motion. In substituting for this, we're going to take an acceleration element being represented as such. And therefore, the element of work done can be given in terms of this specific summation, perhaps from an initial value of 0 to x. And that is going to be giving us the product of mv dv. And then we're going to have all over dx given as that one. And then we're going to have that one represented still in terms of, so this is going to be an integral sign whereby we're going to differentiate, to integrate with respect to x. And of course, we're going to have that one as a dx. So the next element of a dx is going to be representing for the integral of this specific element. But we have taken this particular value of v, which is going to be equated at this particular point. So in this case, we are just going to have this specific version whereby our v has been compensated in this specific case, and that is going to represent our element of our work done. So as you can see, these are going to be the same factors. Therefore, we're going to have this specific element of or the work done given in terms of mv dv given as that one. So if we consider perhaps the change in, of course, this specific aspect of velocity. So we're going to differentiate with respect to velocity. So if we consider the change in velocity from the initial to the final one, therefore this element of work is going to be given as, so mass is going to be constant. So according to the laws of our integrals, we're going to take it out. So this is going to be the integral from the initial to the final velocity of this specific, of course, value given over v dv. So for us to find an integration of this one, we're going to have this one given as a normal integral given in terms of this particular representation of v squared all over 2 from u to v. And this is going to give us the element of work done in this specific case. So this basically is going to represent work done in terms of the change in a half. So this is going to be a half mv squared minus a half mu squared, which basically is still a representation of the work done, giving us the same result as the previous evaluation which we had done. And this is going to be the change in kinetic energy being given as such. So assume that we have understood how we can represent the element of work using various approaches that we have done, especially in our previous video and this one. And that is going to be summing up on how we can, of course, evaluate the concept of work in case we come across it using the different concepts which we have learned in our previous video and this one. So assume that that is going to be comprehensive. So kindly catch us in our next video as we're going to look at the next two aspects of this aspect of energy and power. And of course, that is going to be assisting us try to evaluate the whole concept of the three aspects of work, energy, and power as I've been saying. So that is it for now, guys. By God bless you. Catch us in our next video.